Hey, this is Stereo Police back with part 2 of my Klipsch Forte 3 review. And I was going to dive right into my impressions of the sound of the Forte 3. However, I'm going to put this camera on a tripod here. However, I'm not quite finished with my notes and my positioning of the speakers, the toe end, and various other little nuances that I want to do, including possibly moving them a little closer to the rear walls and many things like that. That I wasn't quite ready to get on with the my listening impressions yet. It's coming up real soon. However, I did feel like, for some reason, making a video today. That doesn't always happen, so I figured, okay. Rather than make a video about something unrelated, I will just carry on with the Forte 3s and provide a discussion of compression drivers. And this is pertinent to the Forte 3s and, for that matter, just about every other Klipsch speaker. And I made a few notes, and I'm fumbling through my notes right now. My apologies. Compression drivers are really at the heart of the Klipsch sound and many other horn speaker manufacturers. Any speaker can be horn loaded. I'm just going to put a picture up right here of a compression driver attached to a horn. Any speaker can be horn loaded to improve efficiency. Klipsch, in their Klipsch horns, and La Scala, I think, they horn load the bass driver, the woofer. Drivers can be front loaded or rear loaded. In other words, you could front load the horn so that the sound pressure wave emanating from the front is horn loaded, or you could rear load a horn. Instead of a bass reflex enclosure, you can provide an enclosure that essentially takes the back wave of the woofer and horn loads it to couple it to the ambient air. But relevant to the Forte 3, the Forte 3 has a horn loaded compression driver, mid-range unit, and a tweeter. And I really love the sound of properly implemented horn loaded speakers, and there are many characteristics of horn loaded speakers that are just really incredible when done right. And just to name the most important ones to me is just the ability to produce realistic live sounding transients, unlike any dynamic driver can even approach. Very low harmonic distortion on a horn loaded compression driver. Very lifelike sound, and also very directional sound that could be beneficial in your room, and I'll get to that a little bit later. But just the lifelike, the dynamics, and the fact that when you're sitting in that sweet spot and those horns are, properly positioned and aimed at you, you actually feel like you're in the speaker. Instead of in the room listening to a speaker, you feel like you're in the speaker itself, and in effect you are. You're kind of sitting in the horn. And when done properly, horn loaded speakers are just absolutely incredible, and they do things that dynamic drivers just can't do in their wildest dreams. So I thought I would cover what a compression driver is, what the horn itself does. Okay, there's two parts. There's the compression driver here, that's actually the speaker itself, the dome, and then there's the horn, and the horn is a transformer, basically. It's an acoustic transformer. But before I get into that, let me just, while I'm on that, I'm going to cover a couple of, again, not very scripted here, but horns have, because I was discussing their advantages, again, I didn't mention this, but another advantage is they're highly, highly efficient. The sound SPL, the sensitivity of the Klipsch Forte 3s is 99 decibels with basically 1 watt input. 2.83 volts into an 8 ohm load, 1 watt. Most average dynamic speakers hover around 85 to 87 decibels per 1 watt. And the decibels is a logarithmic scale. So when you bump up sensitivity by 10 dB, you're basically describing a speaker that is 10 times more efficient, meaning it needs 10 times less power to produce the same output level as the other speaker. So the Klipsch Forte 3s would need 10 times less power to produce the same output level than a speaker rated at 90, and 90 is actually efficient, and 100 times less power to produce the same output level as a speaker rated at 80. So you get the idea. Very, very efficient. Compression driver horn combination can do that. I did mention, I'll just get into this now since I don't have a script. I've drawn a little horn here, and the sound from a horn is directional. So when you are towing in these speakers, you are towing both of them in so that you're sitting within the cone of the horn, and that can provide benefits in the sense that, I've drawn this here, because they're directional, you don't have a tremendous amount of high frequency or mid-range energy emanating out, hitting walls, and then coming back at you. So you get less reflected energy. That can be considered a positive thing, because you're actually listening to the speaker and not the room. It can be a negative thing sometimes when you actually want the room interactions, when they can become beneficial to add ambiance to the music, to the sound. But you are listening to more of the speaker rather than reflections. And horn-loaded compression drivers, far, far less harmonic distortion added to the music. We often concern ourselves with harmonic distortion with respect to audio components such as amplifiers and other things, preamps. And you know, modern amplifiers, 0.01, 0.001, 0.005%, very, very low. But speakers are the #1 source of harmonic distortion in an audio system. They can be on the orders of 5% or more. And that's ordinary and customary, and that's why speakers are so different from each other. That's one of the reasons they're so different from each other. They sound so much different from each other. Well, they're adding a character of their own in the form of harmonic distortion. That could be a good thing. Maybe you like it. Maybe you like the particular character of a speaker. Maybe it's a bad thing. But horns, far, far lower harmonic distortion when implemented properly. On the downside, some horn-loaded speakers have, well, quite frankly, they sound like horns. They sound like, you know, there's a throaty sound, and, you know, like when you cup your hands over your mouth and you shout at somebody. The megaphone sound. And that's why over the years there's been quite a bit of research done, still being done, but about the shape of the horn and the characteristics of the geometry of the horn itself to try to eradicate some of that. Part of that also is those effects are a result of the phase plug inside the compression driver that I'll get to in a minute. One of the downsides of a horn-loaded speaker is, just as I drew right here, they are directional. So, you know, you're fantastic when you find that sweet spot, but if you're going to walk around the room or be in positions outside that sweet spot, the speaker will dramatically change its character, and the mids and the highs will taper off. That could be considered a negative depending on the need for your speakers. Are they party speakers where you want everyone to hear sound all over the place equally, or are they critical listening speakers, that sort of thing. And compression drivers and horns are much, much more costly to design and manufacture. Many more components, many more critical components inside of a compression driver with tighter tolerances, and some more exotic materials are needed, and so they're more expensive. Now, however, when implemented properly, compression drivers and horns are extremely lifelike, extraordinarily dynamic, super low distortion, and they are directional, which can help reduce the effects of room reflection. I'm reading some of my notes that I jotted down earlier today. So let me start out with just briefly discussing a standard. What I want to get into ultimately is how a horn does all this. How is it so efficient? Why is it so efficient? Why is the distortion so low? You know, the character, what makes it tick, so to speak. And it's so fundamentally different than an ordinary dynamic driver that it's worth getting into before we get into how it ticks. Now, and you know what I forgot to mention up front, this discussion again is technical. I didn't want to get into the sound today and felt like making a video, so if you want nothing more than the sound portion, the listening test portion of this review, you might want to skip this video if you haven't already done it. But I find this stuff fascinating, and I know others do who subscribe to my channel, so I thought it's worth getting into. So let's start out with an ordinary, I have a, you know what, I printed out something here rather than draw it. Yeah, there we go. An ordinary dynamic driver. Ordinary dynamic driver is your, basically a voice coil moving through a magnet coupled to a spider, a cone, or it could be a dome, okay, either one, a cone with some surround at the edge tied into a basket. And of course, when current flows through the voice coil in one direction or the other, it either pushes the cone out or pulls it in, creating sound rarefactions or compressions, making sound. Now, the acoustic, and I'm going to get into more of this in a bit, but the acoustic impedance of the cone itself, I'll call that ZA, is super high, whereas the acoustic impedance of the air is the load, ZA, low, is low. And so we have a mismatch between the acoustic impedance of the driver itself and the air, a gross mismatch. And that mismatch causes the dynamic drivers to be extraordinarily inefficient, and hence it requires a lot of power to produce just a little bit of sound pressure. And the more power you apply to a cone or a dome, the more it has to move, the more you get cone or dome breakups and modes and distortions, things like that. And I won't get into that, but this inefficiency lends itself to some of the problems with cones and domes, with distortion and gross inefficiency, the need for a lot of power. And that is because of the mismatch of acoustic impedance between the device itself and the air. And this takes us to a key concept that's involved here, and unfortunately I need to get in just slightly into this concept for a full understanding of how compression drivers and horns work. I could actually just brush right by it, but I'm not going to because I don't feel like it. I feel like actually describing it. And that concept is maximum power transfer. And the way I'm going to describe it, if you already know this, you might want to skip forward, but there's really two concepts at play: maximum power transfer, and there's a concept of maximum voltage transfer. And in a system, let me give you examples of each. Most of our components that we hook to each other, whether it's a power amplifier to a speaker, whether it's a CD player to a preamp or a preamp to an amp, we seek to achieve maximum voltage transfer. And to achieve maximum voltage transfer, I'll give you an example. We have a source, and this source could be anything, but let's just say it's a power amplifier. And we have a load, and the load would be a speaker. But this could be a preamp, and this could be the input of an amp. It could be anything. It's all the same. So for maximum voltage transfer, you want your every source has an internal resistance. Now, since I'm using a power amp, I'll give you an example of a typical power amp output resistance. Okay, you can model a power amp as a, for example, as a voltage source plus its own series resistance. That would be the output impedance or resistance of the amp, and typical amplifier could be 0.02 ohms. So for maximum voltage transfer, you always want the series impedance, the characteristic impedance of your device, to be at least 10 times lower than the load, and you can see we have that here. And the theory makes perfect sense, because if you have this situation, I have 10 volts right here, and I have a 0.02 ohms and 8 ohms, you can use, look at the voltage drop here. Almost all the voltage will be dropped across the 8 ohms, very little across the 0.02. You can see that if RS was super high or the load was super low, you could end up dropping 50-50. That's not good. So for maximum voltage transfer, RS wants to be 10 times or more, preferably, lower than the load. And that's the case with almost all modern electronics. That's what we do. We seek maximum voltage transfer. The output of a preamp might be 100 ohms. Let's say and the input of the amp would be 47K. No problem. Good for maximum voltage transfer. However, in certain systems, including acoustic systems, and also this relates to tube amplifiers coupling output tubes to speaker load, what we seek is maximum power transfer, which is fundamentally different. For maximum power transfer, same scenario, but what we seek here is for RS to equal RL. So RS must equal RL in order to transfer the maximum amount of power. Now power, up here we worry about voltage. Power is more concerned with current, so to speak. So just as a very quick, and I've already done this, so I wouldn't have to do it in front of you here. I'm doing 3 scenarios. I'll explain each, and this is an explanation of maximum power transfer. So we have the same kind of system. We have the source of our signal, and we have a load. We can't change the source. The source is constant. It has got its own characteristic impedance. It's not going to change. The load can change, and often does. So real quick, 10 volts, 10 ohms, 10 ohms. The total power through the dissipated by both resistances is 0.5 watts. Okay, that would be 10 squared divided by 20 ohms. V squared over R, right? 0.5 watts. These resistances are equal, so each resistor is going to dissipate 2.5 watts. Why did I say 2.5 watts? 0.25 watts. Okay, I had to scratch out this. I don't know why for power total I put 0.5 watts. 5 watts. So each resistor being the same value dissipates 2.5 watts. Okay, you can run it a different way. You can take the total current through the system, 10 volts divided by 20 ohms, 0.5 amps. 0.5 squared times 10 will give you 2.5 watts. Okay, now let's do the same thing, but let's switch the load. Let's increase the load from 10 ohms to 100 ohms. Okay, when we do that, all of a sudden we have a much greater load. We have a total of 110 ohms, so the current is dramatically reduced to 0.09 amps. So the power dissipated by this resistor is 0.09 squared times 100, which will give you 0.8 watts, a dramatic reduction from 2.5 watts, right? Let's reverse it. Instead of increasing the load, let's decrease it to 1 ohm. Same scenario. Exact same scenario. The current still, well, actually in this case, my apologies, not the same scenario. In this case, the total load is now 11 ohms as opposed to 110 here or 20 there. So we've actually reduced the total load, so we've increased the current to 0.9 amps. However, that doesn't offset the fact that we've dramatically reduced this resistor from 10 to 1. So 0.9 squared times 1 is 0.8 watts. So what you end up is a curve with is a curve right here, and the curve plots the load resistance. Okay, and this point right here is where RS equals RL. The load resistance versus power max, and you peak power max is where your source equals to your load resistance. Goes down on either side, as you can see. That's maximum power transfer. That becomes important because that's exactly, let me go back to our, this horrible diagram I drew earlier. So with our dynamic driver, you could, I'm using some liberties here, but you could model basically this speaker driver as, just like we did before, as some kind of an energy source with its own resistance. And you could model the air as a load. And what we seek for maximum efficiency is exactly the same. This is the same with respect to acoustics or mechanical, electrical, optical. It's the same principle. What we would seek to do is try to match this internal resistance, which is characteristic of the device, with that of the load. However, it is way mismatched with a standard dynamic driver. Again, standard dynamic driver, this is high and this is low. High and low. And we end up with a scenario similar to this guy right here, where we have the 10 ohm and the 1 ohm. So 0.8 watts as compared to 2.5 watts power transfer with the same input when we had an impedance matched source resistance and load. Now, I'll skip to ultimately what I'm going to get to, and then I'll go back to it and get to it in increments. A horn loaded system, and I'll just draw a dynamic driver here, but I will, now I'm going to draw a dome. Say we have a dome. If I couple that dome, I drew a really bad horn, but to a horn, the purpose of this horn is to match or better match the impedance, the low impedance, acoustic impedance of the room to the high acoustic impedance of the diaphragm itself. And this horn is basically a transformer, and it does something very similar to what a transformer does in a tube amplifier. Okay, this is essentially a transformer, essentially an acoustical transformer. And in a tube amplifier, we're matching the high impedance of a vacuum tube to the low impedance of a load. And I'm going to come back to that. That's what a horn is. That's what it does. And by doing that, we increase the power transfer. We never get 50-50 like I just talked about, okay? But we head in that direction. So what we're doing with a horn is we're heading up the, heading up the hill here, closer to our ideal situation where we've matched impedances for maximum power transfer. Okay, so let me throw something on the table here. Let's look at what a compression driver is this is a depiction of a compression driver without the horn itself. And there's a little opening here with a screen on it. Usually they have screens on there to keep bugs and certain debris, hair, dust out, because there's a lot of intricate little components in there, little channels, fine little things that you want to, you don't want ladybugs and ants crawling up in there, so to speak. So usually there's a screen on there, and everything else in here is sealed. That's the only opening. Okay, let's look at a cross section. I pulled this off the web and I thought it was a pretty good depiction. So what we're looking at here is cross section of a horn coupled to a compression driver. Now, as you can see, with your standard ordinary, I'll draw a dome tweeter, voice coil, a dome, and some surround on the outside, right? And then there's a magnet back here. And out of the dome tweeter, you get sound directly coupled to the air. Again, very inefficient, high acoustic impedance, low acoustic impedance of the air. You can see with a compression driver, many, many more parts. Not many, many, but more. What we have in the compression driver is, in essence, starting with the diaphragm. The diaphragm is the dome itself, and it's usually inverted. The convex portion faces backwards, not forwards like a regular dome. So we have the diaphragm, typically made out of titanium or some certain hard plastic materials, or beryllium, some other exotic materials. It wants to be as hard as possible. I won't get into those reasons, but typically the harder the material, the less breakup you're going to have, and the faster sound travels across the surface. Now, this is the voice coil right here, attached to the edges of the diaphragm, just like in a typical dynamic driver. So when one applies a signal to the voice coil, the diaphragm itself, just like a dome, will vibrate and create sound. Just like a dome, let me draw the back of the diaphragm by itself here, okay? It's just like a dome. Well, you know what? I got a low battery indicator popping up on me here, so I'm afraid I'm going to hit pause here before my camera dies and come back to this. Okay, I had to plug my camera in. Just like a dome, the diaphragm, sound will travel from the edges. Okay, with the voice coil, the force goes that way and that way, right? The force produced by the coil and the magnet. Well, the whole dome itself doesn't move in unison. Sound will actually travel across from both sides, all directions, across the surface, like a transmission line. And at each, and this gets a lot more complex, and I'm not going to get into ultra complex, but know this: at each point, you can just pick different points on the diaphragm itself. It's going to be radiating sound, depending on whether at that point, as the sound is traveling, is it a low point or a high point in the signal, compression or a rarefaction. So you're going to get different wave fronts coming off different points, and they're all going to jumble up and get mixed in with each other. And these wave fronts are going to be out of phase with each other, because for a couple reasons. Number one, the dome is curved. So, and by the way, sound at, for example, 10 kilohertz is a wavelength that's only a fraction of an inch, like a tenth of an inch. Okay, so they're leaving different points at different times, and different spatial positions. So they're not necessarily going to line up with each other. Okay, so you're going to get some out of phase things happening. And not only that, it takes time for sound to travel. So, you know, at this point right here, sound is at this point, now it's emanating here. It takes time to get up to here, and then, so you get a time delay. So the point is, you're going to get all these jumbled mixes of phases. And you couple that with the fact that there is some modes itself, which is some resonance on the diaphragm. It's going to be a jumbled mess, so to speak. It's really not that bad, but there's a lot to correct there. So what we're going to do is we're going to need a phase plug, and phase plugs, that's what's in orange here. A phase plug serves to correct a lot of this jumbled mess. I'm going to take some liberties and make this a lot simpler. But a phase plug has a couple of key purposes in a compression driver. Oh, by the way, I should have said this earlier. Why is it called a compression driver? Well, take a look at this diaphragm and look at the diameter of it, or the area. Look at where the sound emanates from, right here. Where's my picture? Okay. So this portion right here is this little opening here. The diaphragm, probably in the back of this compression driver, is twice the size. Which means it's more than twice the area. What happens when you take air and it's moving at a certain speed, and you compress it into a smaller area? Well, you've compressed it, and also not only have you compressed the air, but the speed of the air has to increase, because the same amount of air entering it has to leave. So it compresses the wavefront. There's literally a higher pressure right here at the exit of the compression driver, at the entrance to the throat of the horn. Throat of the horn, mouth of the horn. So let's get back. So you get all these little wavefronts leaving. Phase plug is a series of, it's a plug that pretty much blocks almost the entire surface of the diaphragm, except it has a bunch of little channels, little slots that sound gets to enter. This is a better depiction right here. Well, not quite better, but you can see we have our diaphragm, or I turn it that way, but it's really upside down. We've got our diaphragm will be back here, and sound will enter these little channels and direct them all to a much smaller area. Again, additional form of compression. Another thing that the phase plug will do, it will serve to correct the wavefront, correct some of the phases. Remember, at each little point on the diaphragm, sound is leaving at different phases at different times. So through the geometry of these channels, it helps to serve to correct some of those phase irregularities, so everything emerges from the phase plug in a more coherent form. And again, depending on the geometry and the construction of the phase plug, you can do different things to meet different needs, but that's in essence what it does. So twofold: further compression, also wavefront correction. Once sound gets to the output of the compression driver, it meets the throat of the horn, and of course the horn will, as we go up towards the mouth, will expand in area to meet the air. This whole system is a transformer. So let's start with the diaphragm. We have a high acoustic impedance. Let's start with the air. We have a low acoustic impedance. We need a transformer, basically. And what that transformer is going to do is it's going to reflect this low impedance back to make it appear to be higher. And just drawing, and you can't even see it. It's going to reflect this low impedance back to make it appear to be higher. And it does that, and you can kind of it's almost intuitive. So we have this high impedance here, at the exit, we've compressed it, so we even have a higher, impedance at the exit of the compression driver entrance of the horn. So all this diaphragm sees is this super high impedance load right here, and it's happy. It doesn't know what's out here. It just sees this high impedance load, and what we end up getting is closer, our RS, okay, the load right here is going to be the opening. So our RS, our inherent acoustic impedance of the diaphragm, is going to become similar to or closer to our load impedance, hence maximum power transfer. The air out here, looking back, you can run it in reverse. The air out here, all he sees is a nice large opening with lower velocity air moving through it and a larger opening, and it sees what appears to be a low output impedance. Doesn't get to see what's happening back here. So it works both ways. We've matched the impedance of the air to a low impedance of the exit of the horn. We've matched the high impedance of the diaphragm to the high impedance of the exit of the compression driver. So we're getting closer to a maximum power transfer. Same thing, by the way, happens, total analogy, I guess you could say, within tube amplifiers. A vacuum tube doesn't matter what kind of tube it is, has a very high plate resistance, and let's say it can go from anywhere from 2K up to 8K, whereas a typical transistor amplifier, you can model that as something with an output impedance of like 0.02 ohms. So remember, with our transistor amp, 0.02 ohms, maximum voltage transfer, 8 ohms, no problem. Our source impedance way lower. Well, we got a problem right here. Let's just say our plate resistance is 2K, and we know that our load is 8 ohms. We got a really big problem, because, yeah, throwing my papers around here. Okay, what we have here is 2K, 8K. We have something analogous to our situation down here where we had 10 ohms and 1 ohm. Super inefficient. Not going to work. Hardly any power is going to get to the load. And not only that, this would require far more current than a vacuum tube could ever source. So we need to actually match impedances. We need to reflect back this 8 ohms to make it look like 2 ohms. Not 2 ohms, 2K ohms. We need to trick this tube into thinking the load is 2K. Well, real simple to do. That's what transformers do. We do it with turns ratios and windings. And I won't get into the details of that, but with the proper transformer, this 8 ohms will reflect back to look like a 2K ohm load, and everyone is happy. Maximum power transfer. Likewise, and that's looking in the primary side of the transformer. Looking into the secondary side, this 8 ohm load is looking back, and all he sees is an 8 ohm source impedance. So once again, match. Guess what? We're doing something very similar here. We have our high impedance, low impedance air. Collectively, this is a transformer, and it doesn't quite match impedances, but it gets closer to the ideal. And all said and done, what we end up with is a far more efficient coupling of a transducer to the air, which results in all those characteristics of compression driver horn that I just talked about. I think that's, let me see, I'm checking through some of my notes to see if there's anything else I wanted to say about that. Probably not. So just to summarize, sorry, no script, just some notes. Our compression driver coupled to a horn, ultra efficient, and because it's so efficient, requires very little power to produce a high sound pressure level. The cone, I might have already talked about this, but the dome itself, or the diaphragm, has to do very little work. Very little motion needs to be imparted to that diaphragm relative to regular dynamic drivers. And the less mechanical motion that we impart to this, the less you're going to get the diaphragm breaking up, the less you're going to get nonlinear characteristics of that diaphragm. All these things contribute to lower harmonic distortion. And once again, we already talked about the directivity of horns. Horns direct their sound to a certain area, which can be beneficial, might not be beneficial, depending on what your needs, what your uses of the speakers are. So anyway, I've been rambling on. This is probably dread listening to this video, probably fumbling and all over the place, back and forth here. It's not very coherent, but I just wanted to have a discussion of compression drivers and horns. They're fascinating. They're one of the oldest audio technologies. When you think about technologies of the 40s and the 30s, and even before that, even before we had electronics, you'd have a turntable with a needle hooked directly to a horn that came out of the turntable to amplify sound. The first hearing aids were horns. People stuck them in their ears and pointed them out at people to talk into, right? Same kind of thing. So that said, thanks for watching. I'm going to pick up tomorrow or the next day with the audio, with the listening test portion of the Klipsch Forte 3s. Needless to say, they're fantastic. I love them. There are some interesting points of discussion with respect to room placement, with respect to placement, some things that, if you're thinking about getting them, I'll give you a little learning curve. It's taken me a long time to actually figure out where exactly I want them placed, and to figure out what dramatic changes happen when you simply move these things around or tow them in by a fraction of an inch, here and there. And lots of good things to talk about there. So thanks for watching, and I will see you later. Ciao.